Alright, good day students. Today being the 18th day of May 2020, we are here again for our usual online programs. My name is Dixon Dio, one of the chemistry teachers at GNA Schools Lagos. This afternoon we'll be looking at some calculation courses in chemistry for the SS3 that are about writing their senior work. Now, before we get to what is on the board there, permit me to quickly run through some certain things I know some of you have had idea of it in your previous schools, and also those of you that are in GNA schools, you had one or two ideas, but maybe as a result of the lockdown, some people had forgotten most of the things they've learned. Now, in chemistry for WAEC, there is always two parts of the practice. That is the volumetric analysis and the qualitative analysis. That is quantitative and qualitative. The aspect of identification of salts and also calculating the concentration of your known in any given solution you have titrated or worked out. Now, to speed up the process, we'll just run through some of the things. Now, for volumetric analysis, which is always a compulsory question in WAEC, most cases you are expected to, the salt solution you are using, that is the chemical salt, will have been prepared for you and labeled, maybe in your labs or thereabouts. The acid in question you are using it also might have been prepared, and you have them in reagent bottles which you will use in the course of your titration. Now here we have a reagent bottle having dilute hydrochloric acid prepared in it, in this transparent reagent bottle. Then here I have my conical flask. The conical flask, otherwise known as the Eremneas flask, which we will use in the course of the titration. You have a filter paper, then you have a very sensitive balance. Now, your school could as well adopt the triple beam balance that you have to make adjustments, or you are using the very sensitive balance whose reading is as fast and accurate as whatever you are using. Then you have your wash bottles, which we use in washing off some things. Then we have our beakers, the 250 ml beakers. Then from here, we have our salt samples. There are two salt samples here. We have the sodium hydroxide pellets, which is a very strong base. Then here, we have another base, sodium carbonate, anhydrous sodium carbonate, which is a weak base. So in the course of the titration, you all agree with me that you will be asked to titrate an acid against a base. It could be a very strong acid against a strong base, like in the case of hydrochloric acid. This is concentrated hydrochloric acid here, which you have to prepare before you start using, because you can't use it directly from this place. Now, you are having a strong acid, you are titrating against a strong base, sodium hydroxide pellets. And also permit me to reiterate here that when you were looking at different types of substances, probably in your SS1 class, you were taught deliquescent and hygroscopic substances. You were told that some substances, on exposure to the atmosphere, will attract moisture from it and also dissolve in it. That is for deliquescent substances like sodium hydroxide. So what I'm trying to say in essence is that if I bring out this sodium chloride here, I have the sodium chloride pellets in pellet form. I bring some, I'll put them on this filter paper and leave it here for some time. As sodium hydroxide pellets, you will notice that these substances, the pellets you have on that filter paper will start attracting moisture from the atmosphere, and they will finally dissolve in it. So when you look at the filter paper, you see those pellets melting, as you can see there. That means they are drawing up those moistures you have from the atmosphere And at the end of the day, by the time you leave this for let's say a period of 2 to 5 minutes, you will notice that everything will have turned into a solution, and so on and so forth. Alright, having said that, what it means is that, and on this point now, which we are going to look at, we have our retort stand. Then on the retort stand, we have our clamp. We have the burette here. You open up this. This is the burette. Now, for your information, the original bullets we used to know are those ones that have clip here that you use in adjusting them in the course of your titration. But this set of bullets are the new bullets that have balls inside the rubber tubing. So all you need to here, you don't need any clip here. If you look at this place, there's an adjustment, there's a ball inside it. So if I fill this up, all I need to do is press the ball to pave way for the liquid you have inside the burette to drip. So all I need to do is I clamp this here to do a simple demonstration of that. A simple demonstration of that. With my readings facing me so that I'll be able to take my readings. Then you can have a simple demonstration here. And also remember that what you pour inside the burette is the acid. So whatever you are titrating against the base you have in that case. So if you pour your acid, for example, we are taking, let's take this to be the acid here. Let's take this to be the acid. I pour this in. Set to a particular volume. And I have here just 31.0 cm cube. So I'll be able to take the meniscus. My eye must be on the same level with that. Now, in the course of your titration, for those of some people will be asking the question, where is the clip? How will I do my adjustments? No. All I need to do is make sure this is here. I'll adjust a little bit. Ordinarily, in the course of the titration, you should have a white tiles on top of it so that when you are experiencing the color change, you are getting close to the end point. You don't need to, for a student who is titrating, you don't need to be looking at the value. All you just need, your eye should be here, white titrating. You don't have any business with the values on the bullet. It is once you get the end point, the color change, then you can read off with your eye on the same level with that. Now all you need to do is hold on to the ball here and squeeze. Then you can see it. It's coming out. The liquid is dropping. It's dropping. You release. You allow. So this is more accurate compared to the other ones. One of the reasons, the limitations you had with the previous one that uses clip is that after some time, some of them will rust and they will cut off the rubber tubing you have there. But in this case, you just need a ball that does the regulation of the acid inside the bullet. Okay, having said that, let's quickly move straight to, we have some questions on the board here. Because of time frame, we are going to look at the questions together, then assignments will also be given. Now, in the course of this, we said we have alternative to chemistry practical, because after your titration in chemistry, all you need is the average titer value. That is the volume of acid mixed. So the volume of acid you have here is what you are bringing in to do your calculation. All right, let's see example 1. They said 3.5 grams of a dibasic acid were dissolved in distilled water and made up to 250 cm. They just said dibasic acid. So the first thing that comes to my mind is that dibasic. They are not being specific about the nature or type of acid you have. So I have 3 types of acid. I have that is strong acid used in the lab. I have this. And I have that. So from here, the basicity of hydrochloric acid here is 1. The basicity of the acid you have here is 2. And the basicity of the acid you have here is 1. So this is the only dibasic acid I have here. That is conc H2SO4. But here, they did not say concentrated tetraoxide 6 acid. They said a dibasic acid. We don't know what that dibasic acid is. So what it means is that if it's a dibasic acid, the polyatomic ion will be carrying a negative 2 minus if it's dibasic, because automatically the hydrogen that is you are attaching to it here will have a +1 in that case, when they undergo what we call interchange, because the powers are not the same. That is the charges they are carrying are not the same. They go into interchange. That is when this is going to come here. But we don't know. We can't say. We say let's take our solution. Let's take our solution here. Let the dibasic acid be R. I don't know. Let the dibasic acid be R from what we have at that point. Now, if our dibasic acid is R, from that point, this polyatomic ion R will be having a charge of this. And the other one that is the acid, the hydrogen, will be having this at that level. So from here, I'm going to have H2R. That's my dibasic acid. So from here, 3.5, they're giving us the mass of the dibasic acid were dissolved in this. So then we are told here that 20 cm cube of this solution, that means the mass of this dissolved in distilled water was made up to 250 cm cube. So after getting the mass of the acid, it was made up to 250 cm cube using our beaker. So whatever solution you have will be up to the volume of 250 centimeter cube or 250 mils you have there. Now, out of that 250 that are made up of 250 cm cube, 20 cm cube of the solution neutralized. So that means 20 cm cube of that solution, this particular has now neutralized 35.4 cm cube. That is the base of this particular base having a molarity of 0.2 molarity or 0.2 mole per dm cube of sodium hydroxide. So the next thing I need to do is the first question, equation of reaction. My equation of reaction, I have a dibasic acid, I have, what do I have? Sodium hydroxide, NaOH, in the aqueous state, reacting with the dibasic acid, also in the aqueous state. That is a solution of that particular acid or substance dissolved in water. That's what we call aqueous solution. Now, you need to understand one thing here in your chemistry, that most times in senior WAEC, sometimes the equation of reaction is given to you in the question paper. Some you could have the equation of reaction given not balanced, you're expected to balance the equation of reaction before you start solving, or the equation of reaction is given balanced and you're expected to start solving, or better still, you are asked to write the equation of reaction yourself and start your calculation. So all I need to do here is that the polyatomic ion here picks what I have from this place. There's a polyatomic ion, so the hydroxide ion here moves with this element hydrogen, while the polyatomic ion of this one, which is the dibasic acid, goes with the element sodium there. So in your rough paper, you could have something like sodium, a metal, is carrying a charge of +1. Then your dibasic acid here is your R2 minus. The charges are not the same. They go into interchange here. What do you have? You have Na2R. Then this Na2R comes into this place as the first product. You have Na2R in the aqueous state, plus then I'm going to use the element hydrogen here with the polyatomic ion of the hydroxide ion OH. So I'm going to have the OH ion, hydroxide ion, carrying a charge of -1. Then I have the hydrogen ion having that. So two of them react together to produce water. So here I'm going to have H2O in the liquid state. Okay, so I've gotten the two products from the reaction of sodium hydroxide and the dibasic ion to form this and water. Then the next thing is you look at it and see, is the equation of reaction balanced? Because once your equation of reaction is balanced, then there's no point continuing with what you are doing. If the equation of reaction is not balanced, it is your responsibility to balance it, because if the equation of reaction is not balanced, then all the effort you have been making since morning will blow up into thin air like smoke, because the mole ratio of acid and base here will never be the same. Then automatically whatever you are doing will blow up into thin air. So I'll now bring out the equation here. I've done my rough here. So I have sodium hydroxide in the aqueous state reacting with my dibasic acid, also in the aqueous state, to yield Na2R in the aqueous state plus water in the liquid state. So from there, let's take it gradually. 1 atom of sodium, 2 atoms of sodium here. So there is problem. So all I need to do, I just put 2 here for sodium. So that here, this reads 2 moles of sodium hydroxide. And if you want to break it down, that means 2 atoms of sodium, 2 atoms of oxygen, and 2 atoms of hydrogen. Now, let's go to the other side to see what we have. Hydrogen on this side is 2, plus these 2 making 4. But on the product side, hydrogen is 2. So to make hydrogen 4, I will put 2 here. That is 2 moles. Remember that in balancing your chemical equation, you use the trial and error method. So you have, this is red, 2 moles of water, but if you want to break it down, it becomes 4 atoms of hydrogen and 2 atoms of oxygen. So hydrogen here is 4, hydrogen here is 2 plus 2, 4. We don't have problem with that. So let's go to oxygen. Oxygen here is how many? 2. That is 2 moles. 2. Oxygen here is also 2. We don't have problem with that. Then let's go to our R here, which is the dibasic acid, which we are using here. This is 1. And so our equation of reaction is balanced. So from here, my mole ratio will give me, this is the mole ratio of base to acid. Now, you pick from whatever you have in front of this here. You have 2:1. That is 2 moles of sodium hydroxide as the base and 1 mole of the dibasic acid as that. Now, having said that, we have written the equation and they said calculate the concentration of the acid in mole per dm³. Now, from this point, you will agree with me that you have in your question II, this is I, that you have CAVA over CBVB is equal to mole ratio of acid to mole ratio of your base. So from here you have the concentration of acid, C base A, volume of acid, V base A, concentration of base, C base B, volume of base, V base B, then N base A. That's number of mole ratios of acid and the number of mole ratios of it. You don't interswitch them. Ratio 2 to 1 is not the same thing as ratio 1 to 2. They are 2 different things. Then the next thing is I will start bringing out the parameters I have from the question. Parameters, very, very important so that I don't use the wrong parameter for whatever I have. So from here, Ca, concentration of acid. Let's look at the question. Calculate the concentration of acid. That is what you are looking for in the question. Concentration of acid, question mark, you don't know. That's what you are looking for. Volume of acid. Let's go to the question and see. Now, 3.5 grams of the dibasic acid were dissolved in distilled water and made up to this. No. Then 20 cm³ of this solution neutralized. That means the volume of acid that neutralized that particular thing. This is the volume of acid here. Volume of acid is 20 cubic cm. Then concentration of base. Let's see the concentration of base. The concentration of base from the question is given to us here. You have 20 cm³ of this solution neutralized 35.40 cm³ of 0.2 molarity or mole per dm³ of sodium hydroxide. This is the base, sodium hydroxide solution. So that gives us 0.2 molarity NaOH, or is the same thing as 0.2 mole per dm³. Remember, your mole per dm³ can be written as mole dm³ raised to power -3 or mole slash dm raised to power 3. You are still very much correct. The volume of base. This is the volume of base. You can see the volume attached to the concentration of the base. This is the volume of the base here. 35.40 cubic centimeter. Then number of mole ratios of acid. Mole ratio of acid we did here. This is the acid here. This is our acid here. 1. I will not make that mistake by writing this one. This is the base. This is the acid. The mole ratio of my base. The base here is 2 moles here. I have 2 here. And I'm good to go. Then it is very, very important for you to understand in senior WAEC that All this will be marked step by step. So if you are asked to calculate the concentration of acid, you are expected, the marker is expecting you to make whatever unknown you are looking for here the subject of the formula. So let's go. We have CaVa over CbVb is equal to mole ratio of acid over mole ratio of base. Are we there? So from here, if I cross multiply here, I have CaVa NB, that is this multiplied by this multiplied by that, gives me CbVb NB. Now what are we looking for here? We are looking for concentration of acid Ca from here. So from here, we divide all through by this, eliminating the whole of this so that we are left with this Va and B. So what do we have? CaVa NB over Va NB is equal to CbVb Na over Va NB. Va NB from what we have in the question there. So this cancels this cancels this. Then we have here that we have our Ca is equal to CbVb Na over Va NB. Then at least you get your mark for doing this here. Then you can slot in the parameter values for each of them. The concentration of base here, Cb is 0.2, so I write 0.2 times volume of base here is 35.40 times number of mole ratio of acid is 1 over volume of acid here is what? 20 multiplied by number of mole ratio of base is 2. Concentration of acid, unit very, very important, mole per dm cube. Very good. So from here, I will multiply out to see what we have. We'll multiply out to quickly see per dm cube. 0.8, is that not so? Over 40. Please divide this, what do you have? 0.177. Now, concentration here, you need to understand one thing, that if you are looking for concentration, the standard that is required for WAEC is you leave it in 3 decimal places. So this is 0.12, this is in 3 decimal places, mole per dm cube. We've solved that question now. The concentration of acid, now say therefore, concentration of acid Ca is equal to 0.177 mole per dm cube. That's the answer to that question. Now, the question that is attached here, we should find the molar mass of the dibasic acid. Molar mass of the dibasic acid. That is when you are able to come to this. Remember that in the course of the calculation, you said that 3.5 grams of a dibasic acid were dissolved in distilled water and made up to 250 cm3. So that means 250 cm3 contains what? 3.5 grams of dibasic acid. Yes, because that's the mass of that you dissolved and made up to that. Then 1 cm3 will contain 3.5 divided by 250 grams of dibasic acid. Then therefore, 1 dm cube, which you will convert because you are using cm cube there, as 1000 cubic centimeter, will contain 3.5 over 250 multiplied by 1000 over 1 grams of the dibasic acid we have in the question here is this, of this H2R. So 250 and 250, 1. 250 and 1000 is 4. So what do I have? I have 3.5 times 4 grams of H2R. What would that give us? Let's see, 14. This is 14.0 grams of H2R. So that's the mass. That's the molar. Now we have to find the molar mass of the substance. Thank you very much. So we'll clean this one now to calculate our molar mass. Now you recall that there is a relationship. Recall that there is a relationship that coexists between molarity, that is molar concentration, mass concentration, and molar mass. So you have here that molar concentration, otherwise known as molarity, is equal to mass concentration over what? Molar mass. So the molar concentration is always given in mole per dm cube. The mass concentration is given in grams per dm cube, while the molar mass of the substance in question is what you are expected to do. Now, what are we asked to do? I've wiped up that place. Let's see. What are we asked to do? I'm so sorry for the question. We're asked to find okay. So from here, what's our molar concentration from here? We have our molar concentration to be this of the acid. The mass concentration of what we're looking for. This is the mass concentration. That is 14.0. This one is read 14.0 grams per dm cube. Why they say 14.0 grams? Because you have dissolved it in 1 dm cube of that. So also have it at the back of your mind, students, that this 14.0 is something as 14.0 grams per dm cube. That is your mass concentration. So molar concentration here, you just slot them in. This one is 0.177 is equal to mass concentration is given to us by 14.0 over molar mass is x. We don't know what our molar mass is. So let's cross multiply. 0.177x is equal to 14. So your x here will give you 14 divided by 0.177. What's that going to give us? 14 divided by that. 9 point what? 096. We can approximate this that x is maybe 79.1 grams of that particular thing. That's grams per mole. That's it. Okay? So we've been able to look at the very first question we have there, and I want to believe that you all know what to do. So the second one, we've been able to calculate, we have to resolve that problem. The second one is that a student was required. Now, you look at this place, please, class. Remember when I told you that immediately you release this into the air, it absorbs moisture. You can see that the filter paper is wet now, showing that the substance is absorbing moisture from the atmosphere. And if you leave this for the next 5-10 minutes again, it will turn completely into a solution. That's why you say that the sodium hydroxide is a deliquescent substance. And the substances that when exposed to the atmosphere will absorb moisture and dissolve in it. They are quite different from hygroscopic substances. Hygroscopic substances are the opposite of deliquescent substances. Hygroscopic substances will absorb moisture, but they will not dissolve in it. Okay, let's look at question 2. A student was required to standardize a solution of HCl using 0.125 mole per dm cube Na2CO3 solution. That is your weak base. The student titrated the acid against 20.0 cm3 portion of the base, that is Na2CO3 solution, using phenolphthalein indicator. Now look at the very question. The very first one, it said, using an assumed titer value, that is volume of acid here, 25.45 cubic centimeters, determine the concentration of the HCl solution in mole per dm cube. Then B part is calculate the mass of anhydrous. That means an anhydrous salt, like we have here. If you look at this place, this is anhydrous. Anhydrous here in chemistry simply means a salt without water of crystallization. That's what you call anhydrous. Anhydrous. When you have a salt that contains water of crystallization, you call it a hydrated salt. I hope I'm communicating. We have so many anhydrous salt like we have here, Na2CO3 anhydrous. Then we have hydrated salt like Na2CO3.10H2, that's your washing soda, and so on and so forth. B. Calculate the mass of anhydrous Na2CO3 required to prepare 250 cubic centimeters of 0.125 mole per day in Na2 solution. You are given the atomic masses of the elements you have that make up that particular base: carbon 12, oxygen 16, and sodium 23. Let's quickly look at that question as we round up for today. Student was required to standardize a solution of HCl using that. So if you look at this now, the first thing I need to do here is to first of all write my equation of reaction. Solution is my equation of reaction. Anything I'm doing without equation of reaction in chemistry is like the person is just making a mockery of himself or herself, because you won't even be able to go anywhere. And to have the equation of reaction, you cannot react, you cannot balance, then it becomes an issue. The person gets stuck there forever. So we have here then ability to be able to bring out the base and the acid that is reacting in the question. Here we have a base Na2CO3 reacting with hydrochloric acid HCl. So the equation of reaction, we have Na2CO3, a base in the aqueous state, reacting with HCl in the aqueous state. This is another thing all chemistry students must learn. It's not the issue that the product just came from the moon. And what if what you have here, you have the product X plus Y plus Z, and you don't know what the products are, you say, that is how it's written, write it like that. No, it's not the issue that that's how it's written. You must be able to deduce the product form from that. So in deducing the product form, the first thing you need to do as a science student is that I will first of all marry the likely things I need to understand. Now from here, this is a compound, this is another compound. Now the elements in this compound, there are 3 elements in this compound: sodium, carbon, and oxygen. So the first element you have here, sodium, picks the radical of the acid in question. So here, sodium picks the radical of the acid, that is Cl minus, and I'm going to have sodium here is carrying sodium is a metal in group 1 of the periodic table, the alkali metals, which are very, very reactive. So reacts with the radical, the chlorine, that is the chloride ion, is carrying a charge of -1. So when the charges are the same, +1 minus 1 is what? 0. So this and this will cancel out. Then the first product that will come here is my common salt, NaCl. Plus, then I'm left with this now. I'm left with hydrogen. And this. Now remember what happens to all triazocarbonate when you are subjecting them to heat. What it means is that if I break this down by disintegration, or better still by thermal decomposition, you will agree with me that hydrogen will pick one element of oxygen from here. If it picks one element of oxygen, you have hydrogen +1. Then oxygen is carrying a charge of -2. So it picks one element from the 3 atoms of oxygen you have here. So the charges are not the same. They go into interchange. And what do you have here? Water. So water comes in here as H2O, liquid. Then plus, what are you left with here? Now from here, now you have removed one atom of oxygen from the 3 atoms of oxygen you have here. You are left with 2 atoms of oxygen. So you are left with CO2, which is a gas. Then your CO2 gas comes in. So it's not a magic in chemistry, and they will tell you, no, that is how the equation is copied down. No, there are rules in writing chemical equations in chemistry. And as a chemistry student, you must be able to do that. So if the person cannot do this, then the whole thing blows up into thin air like so. So my overall reaction now becomes Na2CO3, that's sodium triisocarbonate 4, aqueous, reacting with hydrochloric acid in the aqueous state, that's hydrochloric acid. Then the first thing I have here is NaCl, aqueous, plus water, liquid, and plus CO2 gas. I've been able to deduce the three components, that is the product. Then I will now check if my equation of reaction is balanced. If it's not balanced, I'll balance it before I start moving. 2 atoms of sodium, 1. So to make this balance, I will put 2 here. So I have here, carbon is 1 here, carbon is 1 here. We don't have any problem with that. Oxygen is 3 here. Let's see oxygen. Oxygen is 2 plus 1 is balanced, is 3. Let's see hydrogen. Hydrogen is 1 here, hydrogen is 2 here. So to make this balance, I will put 2 here. So this will be 2 moles of hydrochloric acid. Then from here, chlorine also is 2 here, chlorine is 2 here. So let's see, sodium 2, sodium 2. Carbon 1, carbon 1. Oxygen 3, oxygen 2 plus 1, 3. Then hydrogen 2, hydrogen 2. Chlorine 2, chlorine 2. So our equation of reaction is balanced. Then we are good to go. Then mole ratio. Our mole ratio will give us the base 1 ratio the acid 2. That's what we have here. That is the number written in front of the compound is what you pick as the mole ratio. Okay, having done that, we are good to go. Then we will now move. Question 1 is what we are looking for now. CAVA over CBVB is equal to mole ratio of acid to mole ratio of base. What are we asked to find? We are asked to calculate the concentration of HCl solution in mole per dm, concentration of Ca, that's the concentration of the acid. So from here, I will cross multiply. I'm making this subject of formula. CaVa NB is equal to Cb multiplied by that Vb multiplied by N base A. This is what I'm looking for. I'll divide all through by this. So my concentration of acid here gives me concentration of base multiplied by volume of base multiplied by volume mole ratio of acid divided by volume of acid multiplied by mole ratio of base. In what? In mole per dm cube. Remember what I said? Is either you write mol dm raised to power minus 3, or you write mo, if you are putting slash, you are not putting a negative raised to power there, because this one, if you treat this expression on your own, m raised to power minus 3 will give you 1 over m3. Then if you do your mistake, you still come back to that same. Let's see the concentration of acid from the question now. I'm bringing out my parameters from the question. Concentration of acid unknown. Volume of base. Let's see the volume of base from the question. Let's look at here. Concentration of base. The student titrated the acid against 20.0 cmK portion of it. So this is the volume of the base. This to here. That's the volume of the base. 20.0 cmK. Don't make that mistake. Mole ratio of acid and mole ratio of acid here is 2. Okay, volume of acid here, let's see. Okay, using an assumed titer value of this. The titer value is this is 25.45 cubic centimeter. From there, then we have a mole ratio of base. Mole ratio of our base is here. This is our base, that's 1. You write 1 here. Then I slot in the parameters from what I have. Concentration of acid here gives me, okay, concentration of base we have there. What's my concentration of base? I think that Cb. I didn't write my Cb. Concentration of base. We omitted this one here when we wrote this. Concentration of base here. This is my concentration of base. Anything in mole per dm cube, 0.125 mole per dm. Mole per dm. Okay. So from here we have 0.125 multiplied by volume of base, okay, 20.0 times, alright, what do you have? Mole ratio of acid is 2 over, alright, volume of acid here, what's our volume of acid here? 25, that's the titer value, 25.45 multiplied by the mole ratio of base is 1 here. This is in mole per dm cube. Alright, we multiply that out. What do we have? 0.125 times 40.
5.
divided by 25.45 mole per dm cube. Yes, what will this give us in 3 decimal places? Concentration of acid 5 divided by 25.45. That should be around 0. Okay. As 0.196. Leave it in 3 decimal places. Remember, this is in 3 decimal places. That's the YX standard. 3 decimal. Don't leave it in 2. Always in 3 decimal places. So even if you've gotten here, there's nothing here. You just add 0 to that point you have. So that's the concentration of acid. Then look at the next question. Calculate the mass of anhydrous Na2CO3 required to prepare 250 cm cube of this solution. What do you do? What do we do in that situation? What do we do? Or students, should I leave it as assignment for you guys because we've done 2 today, or do we do it together? Because if you recall here, you are going to work with a lot of things. Molarity is equal to mass concentration over molar mass. And in this case now, volume is added to it. What do you do? What do we do in a situation like this? Now, in this place, we are looking for the mass. If you still recall again, the relationship that coexists between N is equal to M over capital letter N, which we have from here. That is, number of moles is equal to mass over molar mass of that, which is equal to number of particles. So your particles could be electrons, could be protons, could be anything, over Avogadro's constant. That's your L. Now you are trying to look at the relationship here. This is concentration C. This is concentration C, 0.12 mole per dm cube. This is the volume of the concentration. The volume of that concentration. Then you are asked to find the mass. So that means this is the unknown here. Then you look for the molar mass of this. What do we do? Yes, what do we do there? To find that concentration is equal to 1000 times the mass over volume multiplied by capital letter N. So your concentration here is 1000, that's 1 dm cube of that, multiplied by the mass over the volume multiplied by the molarity, that's the mole per dm cube. So from this question here, I have the concentration given to me from this place. So I have here that C is equal to 1000 times M mass over molar mass V times molar mass. That's what I have from this place. And this is what I'm looking for. I just make my M subject of formula. If I cross multiply it, C times V times N is equal to 1000 times N. So from here, I have here, divide both sides by this. I have concentration times volume times molar mass divided by 1000 is equal to mass. That's it. So from there, I have my concentration C from the question, which is 0.125 mole per dm cube. Then my volume, the volume given to me V, volume is here, that's the volume. I have 250 cm cube, 250 cubic centimeters from there. Then molar mass of the weak acid, the weak base, sodium carbonate 4. I have here, you find the molar mass. Sodium is 12. You round it, that is 12 times 2. Sodium is 23. 23 times 2 plus carbon is 12 plus oxygen is what? 16 times 3. This gives us 46 plus 12 plus 48 grams per mole. So what do we have here? 46, 12, that gives us 58. 58, 48, that's 106. This is 106 grams per mole. So we are getting very close to it. From here, we now have here, that's N is now equal to concentration 0.125 multiplied by volume 250 multiplied by what do we have, molar mass, which is 106 divided by 1000. Okay, this will be in grams. Okay, multiply this out. Let's see, 250 is 1, 250 here is 4. So here we have 0.125 times 106 divided by 4. Let's see, 4 can 4 go here? Let's see. 4 in 4, 4, 1, 4 in this is 2, that's 8 in 26. No, 2, 4 can go. Let's see, 2, 2 in this is 2, 2 in this is 53. Alright, so what do we have? 0.125 times 53 divided by 2 grams. Yes, somebody to divide that for us. 0.125 times 53. What do we have? 25 divided by 2 grams. And if we divide that by 3, divide that by 2, we're going to get 3.3125 grams, approximately 3.31 grams. 1, 2, 2 decimal places. So the mass is approximately that. So that's it. Thank God for his mercies, for his knowledge, and for his provision. So I'll employ you to pick up past questions and also solve similar problems. Thank you.